Okay, so today's topic is all about circuits. We're going to focus very specifically today on electricity in a circuit. So before I do that, I want to do a quick recap. What makes static electricity different than current electricity? Anyone want to take a stab at it? Go ahead, Ryan. Yeah, you're using your hand in a circle. It's in a loop. It's in a circuit of some kind. Yeah, static electricity is a buildup of charge. Like if you shuffle your feet along the floor and you build up some charge on you, then you go zap your buddy. That's a one-time buildup. Lightning, by the way, is a good example of this. Lightning is a one-time strike. It doesn't go in a loop. It zaps from the cloud to the ground and it grounds it and it's done. We're going to focus today on current, which needs to have a closed circuit pathway. And as soon as anywhere along the way that pathway gets broken, the loop stops. The clock over here, although it's working, I don't know if you guys noticed, but the clock actually died, and I had to put the battery back in. And the reason why is that somewhere within that battery cell that I made with the liquids there, somewhere along the way there, the circuit got broken. I actually think I know why it got broke. I can actually visibly see it. Can you guys see the electrolytes in those three solutions, the blue color? One of them's not blue anymore. And I believe that is where the broken pathway is that the ions are supposed to continue a loop, but that middle beaker is no longer blue. I believe that's why the battery died. That's my best guess. So that's why I had to put like the other battery back in. Because I'm actually going to put it away now. I think I made my point. You guys all got to see the battery at some point. So here's kind of the main thing I want to focus on here. If you want to have a circuit, you need to have at least three things. Okay, and I think this came off of another slide of notes already. The three things at the bare minimum you need in a circuit are you need a battery, you need a source of energy. Something has to be driving the electrons. Electrons don't just move on their own, something has to push them. What's the word we use to describe the energy, the push given to electrons? Yeah, voltage, yeah. Right? A battery has a certain amount of voltage. For example, like a little bitty battery that's in your calculator is about 1.5 volts. Maybe you've seen like a 9-volt battery. It's like about that big. Your car has like a 12-volt battery. Household electricity is about 120 volts. That's the push we give to the electrons. So you need to have something to get them going. That's part one. Part two, you need to have a conducting unit, something that's going to let the electrons flow through it. I cannot think of anything that it would be other than wires. Okay, we usually use wires, and the wires are what the electrons go through. The third thing you need is something that like uses the electricity. It has to have a purpose, and we call that a load. Do you guys remember that word from before? A load. So a load could be a light bulb. A load could be a heating element in a toaster. A load could be a speaker. It takes the energy and converts it into something else. Okay. What we're going to focus on today now is different ways that we can build circuits and do something useful. Okay. So here's a basic circuit, and hopefully you guys can follow along in some of these diagrams. This is a doorbell. Here's how the doorbell works. When you guys press the button, it goes ding dong. Okay. What is happening? Well, it's converting electrical energy into sound when the button gets pressed. Here's why. If you guys can see this, here's one wire coming in like this, and here's another wire coming in like this. And do you see how this little piece right here, how it isn't actually touching? I'm going to try to highlight it right here. Can you guys see how right there's a little gap? This circuit isn't connected all the way. It's coming in through here, and then it wants to run through here and back through the other way, but it doesn't because there's a little space in between. The circuit's broken. Well, what happens when you press in on the doorbell? When you press in on this doorbell, this little flexible piece of metal kind of gets pushed in, and it all of a sudden then attaches, and when you press in, then the circuit runs and it goes ding dong. You pull your finger back off the button, and the spring kind of pulls it back out, and the circuit breaks. In a way, what this right here is, it's a switch. And almost all devices need to have some sort of switch to them, something to turn the device on or off. Otherwise, it would always be running. Right? You guys already know this, right? Like these lights in our room, the only reason why they're on is because I turn the switch on. Right? But like even your cell phone, for example, right? You press the little power button on there real quick and it turns the light off. Right? So almost all devices have some sort of switch to turn power on or off. Here's another diagram I pulled. And if you can kind of see the idea here, it's trying to show you that one of these light bulbs is lit up, but the other one is not. Let's trace the pathway, the circuit of electrons. As it comes from the battery here, it goes through here, through the closed switch, through the light bulb, and back again, which is why this light bulb turns on. But why does the other light bulb not turn on? Hopefully you can kind of see. Yeah, it goes through this switch, it goes to this connector, it then tries to go this way. Oh, but look, this open switch, there's a bit of a gap right here. So although the electrons want to keep going through here and through there, see how there's this gap right here? Well, then it turns it off. Right? So all devices have some sort of switch inside of them. In electronic devices, sometimes we call them transistors. If you've ever heard that word before, where basically it either lets current go or it doesn't let current go through. Okay. Now, when we're talking about a battery, I need you guys to know two other words here. The words are called anode and cathode. And although you may not know those words, I guarantee you know the two sides of a battery, because if you've ever seen any battery before, you know how there's one side that's positive and one side that's negative? Those are the two sides to a battery. So the anode is the negative side of the battery, and the cathode is the positive side of the battery. I wish I kind of switched the way I drew this picture here. Do you guys remember from chemistry? I talked to you about cations and anions. I had a really silly mnemonic device remembering which one is which. Cats have paws. Yeah. So if you need to know which side of the battery is which, the positive side of the battery is called the cathode, and the negative side of the battery is the anode. So I'm actually going to label that. This is the anode. This is the cathode. Now, the way it works is it's really based on separation in charges. Electrons are what moves. Electrons are what flows through the circuit. Now, if all of the electrons are over here at the negative end of the battery, do electrons like being by other electrons? No. Remember how when we had someone go to the Van de Graaff generator, their hair got all staticky? The reason why is that electrons by other electrons wanted to spread out as much as they can. So all of these electrons over here, they want to get away from each other. You know where the negatives would like to get to? To the positives. But what they do, though, is a battery actually has like a boundary between it. So although the electrons would sure just love to go through the center of the battery, what they actually have to do is go through a loop. And so they go through some sort of loop. They then go through some sort of device or load, and then they show up at the other end on the positive side. You okay? I have that same sort of picture here on this guy right here. Remember talking about hot wires and neutral wires? The hot wire is the one that the electricity comes through. So like as you have the transformer in your house, the electricity should be coming through the hot wire, into the plug-in, into your device, back out again. That explains why all devices have two prongs. Does that make sense? You have to have two prongs, because one prong is for the input of electricity. The other one is for the output of electricity. So electricity comes through the hot wire, goes through one prong to your device, back again, and then goes back through the neutral wire. Hopefully we don't need the ground wire, because then you're getting electrocuted maybe, but that completes your circuit. Does that make sense? I've got a picture on the next slide. Yeah, this one here. I got a little animated one I think is kind of cool. What you can hopefully see here is that we've got a switch up here, and as the switch opens up, the electrons stop moving, right? And as soon as the electrons stop moving, the light bulb turns off, right? But otherwise, if the switch is closed, what's really happening here is that this side right here is the anode of your battery. It's the negative side. See how there's a positive right here? This side is the cathode. In a way, this is the hot wire, and this one over here is your neutral wire. And what's happening is the electrons are going away from the negative side, through the device, through the switch if it's on, and over here to the positive side. So here's what I need you guys to be able to tell me. If I ask you about how electrons flow, there's two things you could describe it as. Electrons always go through the hot wire to the device and back through the neutral wire. So go through hot, back through neutral. Or the other way of describing it is you could say that it's going from the anode, which is the negative side of the battery. It runs from the anode through the wire to the device, and then ends up back at the cathode. Anybody ever try to put like the batteries in a device, but you accidentally put it in backwards? It doesn't work if you put it in backwards. You've got a 1 in 2 shot of it, and you're going to get one backwards, right? No, you always get them right? Then you flip it the other way, right? And then it works all of a sudden. So hopefully you guys get the point I'm making here, though, is that the battery always has to be oriented in the way where the negative side is where you suck the electrons out of. It goes from the negative side of the battery around the loop and back to the positive side. Okay? Or hot wire to neutral wire. Do you guys feel like you get this concept? No. Now, one of the cool things is that you can actually have multiple switches. I have one of these in my house. Maybe some of you guys do too. I have a system where if I go hit the light switch over here, it turns on the light. But then if I go hit the light switch way over here, it turns off the light. And then if I go hit this one the other way, it turns it back on. Anyone ever have one of those in their house? Yeah. Yeah. Those are known as like two-way switches. Guys, give me your attention here. And if I could give you a piece of advice, there's actually a question on this on your unit final. And the other class over there, so many of them got this one wrong. So maybe put a star next to the slide, because there's a question just like this on your final test. I want to try to show you in this diagram how a two-way switch works, where like you can switch this one on or this one on and it turns on the light. So let's see if this diagram makes sense. Right now, the light bulb is off. If I'm looking at this one right here, the light bulb is off. And the reason why is that there's no closed pathway. If I were to start here and try to go through and go around and around like this and back up, did it actually complete the circuit? No, so that's why it's off. But, let me just erase that real quick. Let's say that I move one of the switches. So for example, let's say that I move this switch right here and I flick it into the other position. Well, now it looks like this guy right here. And now look, now there's actually a closed pathway. This guy was still in the same spot it was, but if I switch this guy from being down to up, all of a sudden now, as I go through, now you have a complete loop. So what that means then is that if I flip this switch up, it looks like this diagram right here. But that's not the only switch you could use. What if you were to take this switch right here and flip it down? If you took this switch here and flipped it down, you'd actually have this picture right here, where the current would then be running through the bottom of the two loops. Does that make sense? So this is one of those kind of setups where maybe you do this with like your parents. I go hit the light switch over here, turn the lights off, and then they go hit it over here, they turn it off, and then no, I'm turning it on. No, I'm turning it off. You guys know what I'm kind of talking about here? Yeah. I have one of those right now. My back porch light is doing that, and the light is up to turn the light off, and it drives me nuts, but I have to go hit the other one. You like that? Except for that one? Yeah. Okay, now there is one more thing we sometimes do to our light switches I need you guys to know about. Okay. It has two names actually. It's either called a variable resistor. Shh, listen up again, guys. Or we call it a rheostat. And I actually have one of those in the classroom right now. This is groundbreaking. Whoa, hang on. Watch this. Whoa. 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 Oh, look at that. Okay, does anybody have one of those in their house? Either like a dimmer switch or some older ones. They're not like a slidey thing. Thanks. But they're like a little turny twister. That's what this picture is right here. Okay, let me talk again here. So this is called a rheostat. Okay? We also call it a variable resistor. Here's how it works. Let me go back to my hallway analogy of current, voltage, and resistance. You need to get from here down the hallway. Okay? Now, if there's just one of you, that's not a lot of current. If 8 of your friends go with you, that's lots of current. But what slows you down is things that get in your way. Right? So if the hallway is really narrow or there's a bunch of grade 6s all in the way, sometimes it prevents you from getting to your destination. Well, So guys, that's what a variable resistor does. As soon as I press the dimmer on the switch, guys, listen up, please. This is really important. As soon as I moved the dimmer down, I increased the resistance. Let me say that again. As soon as I moved the dimmer switch down, I increased the resistance. It made it harder for the electrons to move. It would be like in the hallways if I told all the grade 6s to go stand in the hallways. Now it's harder for you to get through there, and because of that, the light can't shine quite so brightly because there's something interrupting and slowing it down. It's not broken, but it's slowing down the pathway. If I then put the light switch back up again, I'm decreasing the resistance. I'm making it easier for electrons to travel. Okay. Let me give you some other examples of variable resistors you might know about. For example, let's say that you were to use a hand mixer, and it had like 3 speeds. It had slow speed, it had medium speed, it had ultra fast blending speed. Well, that's a variable resistor because as you change the resistance, it changes how fast it moves. Maybe another good example would be an electric drill. Okay, you know how you have like the electric drill, but you can like change how fast it's working? Like you want to speed it up so that it can cut through concrete and slow it down so it can cut through glass or something like that. Well, if you had a variable motor to it and you could change the speed, that would be a variable resistor or a rheostat. Okay. You guys actually have one of these every time you listen to your phones. Let's say you're listening to music. Where's the variable resistor when you're listening to music? The volume, yeah. Because as you turn the volume up, you are decreasing the resistance so that it can be louder. As you turn the volume down, you're increasing the resistance so that it doesn't work quite as efficiently. Effectively, you're trying to slow down your device. But like by slowing it down, it gets dimmer, or it gets softer, or it gets slower. Does that make sense? So I need you guys to know that term, variable resistor, or also known as a rheostat. Most of you guys are pretty familiar with these in everyday life, though. So I want to talk a bit more about resistors on this slide here. Again, remember the idea of what a resistor does. If voltage is what gives somebody a push, and amps is the current, it's the people who are moving, the ohms, which is resistance, it's what's trying to slow something down. Okay? I need you guys to know that there are 2 types of resistors. One is known as a wire-wound resistor. It looks something like this. I found a picture online so you can kind of see what they look like. Or sometimes you have what's known as a carbon composition resistor. It looks like this. Long story short, it is a device that when you put it in your circuit, this little thing right here is going to slow down the electrons. It's going to prevent the flow of current. Maybe to the point where it doesn't flow at all. When I put those switch all the way down to nothing, the resistor is set so high that the current flow is nothing. So I want to do this one more time here. Here, my resistor is set to its highest or lowest setting. Lowest setting of resistance right now, which is why we have lots of light. As I do this and I turn the lights down, the resistor is getting stronger. I'm adding more and more resistance until I get to the point where there's almost no resistance, or so where there's lots of resistance. This is lots of resistance. This is no resistance. This was a switch. You get the difference? The switch literally broke the entire circuit and turned it all off. Now the circuit's back on, but now I'm adding resistance to it, thereby making the lights dimmer. Hopefully you guys get that idea. Is it too bright? I'm actually going to close this window too. There's some glare on the screen. How's that? I don't want to go too dark. Okay, this is actually a slide right out of your textbook, and by the way, it's actually one of the questions on your next assignment. So for any of you who are ready to start on assignment 2, this is actually a question on your second assignment. When you're building a circuit then, I actually lied to you at the start of class. I said you need 3 things for a circuit. We actually need 4. You need to have a battery source, something to get the electrons moving, to give it a push, a voltage. You need to have something to conduct the electrons, usually wires. You need to have a load. Something needs to do something. But the thing that I didn't talk about then before is you have to have a switch. Why do you need a switch? Yeah, otherwise it'd be on all the time. And I can't think of too many devices where you wouldn't want to be able to, at least if you wanted to, turn it off. Right? Because eventually, either the battery is going to die, or you're just draining energy and you're just wasting electricity. Right? So every device should have that fourth part. So a source, battery source, wires, it does something, and a switch. But what I want to let you guys know is that it's actually possible to have many, many, many more things in a circuit. Here's that little thing that I pulled out of the textbook here. You could have conductors or batteries or lamps. You could also have ammeters and voltmeters. Do you guys remember what ammeters and voltmeters do? Measure current and voltage. Yeah, ammeters measures current. Voltmeters measures voltage. You could even have this symbol right here. This is a rheostat. What's a rheostat? A variable resistor. It changes the resistance, yeah. You could even have this picture right here. This is a motor. If you have a motor, it's like it's converting something to mechanical energy, like a fan, for example, would be a motor. Or this guy right here. Do you guys remember what a fuse is? Courtney. Guys, listen up here. I've only got a few more minutes left, so give me 5 more minutes of attention. Exactly, yeah. So if you ever wanted to draw a picture with a fuse, the symbol is like this and this. You draw a dot on both ends, and this is the symbol for a fuse. So what I want to do last now is I want to show you guys how to build some circuits. And this is actually what we're going to do in our lab tomorrow. So give me 5 more minutes, then I'm done, I promise. Okay. There's actually 2 main types of circuits I need you guys to be aware of. They're called series circuits and parallel circuits. And I actually have a picture of both right here. Okay. This one right here, this is known as a series circuit. And what ends up happening is the electrons go through the circuit. Here, they're going to light up light bulb number 1. They're going to light up bulb number 2. They're going to light up bulb number 3 and keep going. But here's the problem. What happens if this light bulb right here burns out? The whole thing turns off. We actually see this sometimes around Christmas time when we have Christmas lights out. Old school Christmas lights, if you had one bulb that burns out, sometimes the whole string of lights turns off. Anybody ever seen one of those before? Yeah, it's super annoying then because you got to figure out, well, which bulb is the broken one. That's a series circuit where you put them literally all right next to each other. Most often we work with something called a parallel circuit. See how there's still 3 light bulbs right here? But they each get their own pathway. Here, these guys right here have a pathway. I'll do another color here. Then this guy right here has its own pathway. And this guy right here has its own pathway. If this light bulb right here were to break, the other 2 would actually keep working. And so that's one of the cool things about wiring things in parallel rather than in series, is that series has them all in a row. Break one of them, the whole thing's off. You know those 3 batteries that I put right there? The 3 blue cells? I believe the middle one is broken. But because they are wired in series, as soon as one of those 3 things had a broken connection, the whole thing's kaput. But if you could wire them in kind of like, and do you guys, by the way, do you guys know the word parallel from math? The reason why we call this a parallel circuit is because these lines right here are parallel to each other. That's why we call it parallel, is that these lines right here are effectively parallel to each other. If you wire things in parallel, if one breaks, the other ones keep working. And I've got just a couple last pictures to show you an idea here. Okay. Tomorrow in our lab, you guys are going to use a simulator. Because what I discovered is, 1, I don't actually have enough materials for everybody to do hands-on electrical work, and 2, it takes way too long. So I'm going to show you guys an online simulator where we're going to make pretend circuits digitally. And so this would be a good example of one. I've got a battery here, and the battery is hooked up to just one light bulb, and you can see the light bulb is shining quite brightly. Now that's only one light bulb. Now what I want to do is I want to put 2 light bulbs in there. McKinley, Alexa, can you guys pay attention, please? You've been chatting away for like most of my lesson. Can you give me 5 minutes of attention, please? Thank you. Okay, let's put a second light bulb in. Now we have 2 light bulbs. First of all, what do you notice about the brightness of the light bulbs? Yeah, they're not as bright. Here's why. They have to share their electron flow. The electrons are going through this path right here, but some of them get used up here, and then some of the electrons kind of get slowed down here. They get slowed down in 2 locations. And because of that, each light bulb is half as bright. Right? you might notice I put actually an ammeter in here. It used to be 2.5 amps. But as soon as I put in 2 light bulbs, now it's 1.25 amps. It's half as much. The reason why is that each one of these guys right here slows down the electrons. This would be known as a series circuit. If this light bulb right here were to break, the whole thing shuts down. Does that make sense? But we don't usually wire things in series. We usually wire them in parallel. Because here's a parallel circuit. And what's kind of cool about the parallel circuit is it actually solves 2 problems. First of all, take a look at the brightness of the light bulbs again. It's back up to being full brightness. And the reason why is that everybody has their own loop. This light bulb right here has its own independent loop right here. So this light bulb gets its own loop. Whereas the other light bulb also has its own loop. Now I know some of the wires are still shared, but it has its own independent path. If this light bulb right here were to break, the purple loop would still run. Does that make sense? And so because of that, each of them actually has full amperage because they each have their own path. Now, I mean, if this wire right here were to get cut, the whole thing would be broken, obviously. But if right here, this wire were to get cut, at least the other one would still work. What we're going to do tomorrow then is I'm going to show you guys using an online lab. I'll demonstrate it right now before we call it a day. I'm going to show you guys how to build some circuits. So I need you guys to print off this lab before tomorrow. And I've got laptops booked for the class. We're going to go to a website right here. And what it has is an online simulator. Rather than me giving you wires and batteries and light bulbs, this is so much faster and more effective. We're going to play a little, it's almost like playing a little game, I guess. Kids in the last group enjoyed this. What you're going to do is you're going to build your own circuits. I'm going to show you real quick how to build one, and then we'll do it more tomorrow. You're going to want to, like, say, take some wires, and you can, like, stretch the wire and move it all around. You're going to want to add in a battery. You can, again, move it kind of all around. I want another wire like this, and then, say, like a light bulb. And if I do this, now the light bulb turns on. Right? And then you can do all sorts of interesting things. Like, for example, you can put a resistor in. And as soon as I put the resistor in, all of a sudden, as I change the resistance, as I up the resistance, see how the light bulb gets brighter? But now as I decrease the resistance, that's like changing the brightness, changing the resistor. Or I could put in a switch. And right now, the switch is open, so it doesn't work, right? As I toggle the switch, now it works. And then you can play around and like add a whole bunch of things. So some kids, it's almost like I give them Lego to play with, right? And I just say, well, start building stuff, see what you can do. If you keep going down on the list, they even give you weird things like a coin. If you'd like to, you could see whether a coin can conduct electricity. Okay, so it can. Or the eraser. Hey, let's do a quick bet. Who thinks the eraser will conduct? Who thinks the eraser will not conduct? Yeah, the eraser is like a rubbery compound. Rubber stuff doesn't conduct, so that shouldn't conduct. All right, well, let's try this one here. Pencil conducts or doesn't conduct? But look, it's only a little bit, because maybe it's not a really good conductor, but it conducted a bit. Right? So, and then what you can do is you can add multiple things. For example, you could add in an extra loop. You could add in a second light bulb right here. You could add in an extra battery. I think it's a bigger battery. That's why they've got 2 different sizes. Yeah. Now, it's actually possible sometimes to have it running a little bit too high. What happened here? Why is it on fire? Pause for a second here, guys. Why is it on fire? There's so much current, there's so much friction that eventually those electrons are heating up and heating up. They're going to actually light on fire. But we have a fail-safe against this. What's the device we usually put in here to prevent this? A fuse, yeah. If you put a fuse in here, the fuse would melt and prevent a fire. So, okay, anyways, here's what's going to happen then. Tomorrow, I'm going to have laptops for you guys. I'm going to walk you through how to make some circuits. Guys, listen up. I'm done. This is my summer here. But I want you guys to explore building some parallel and some series circuits and kind of see how these work. Okay? Rather than doing it, though, hands-on with wires and batteries, it's a lot faster if I give you a simulation. Guys, you're not listening here. I'm almost done, I promise. Okay. But can I ask you guys to do one thing in advance, though? Can you print off the lab before class? The reason why I really need this done in advance is because if you're trying to print it as we're doing it, we're wasting time. And I only have one class with the laptops. So I'm done today, okay? I finished with like a half an hour plus to go. Let me give you some last thoughts. Print off tomorrow's lab. Finish your old assignment. Mark it yourself. Print off the new assignment. You should be able to do a bunch of questions on it. You've got a lab that's old to work on. There's a lab that's new to work on. Don't waste this time, okay, guys? You've got half an hour today. You're allowed to go and scatter if you want. But my advice is don't waste it. Do something productive today. Sound good? Okay, I'm done. Half an hour.